density functions. So a density function is going to give us a model that's going to give us information about how a particular characteristic is distributed within a certain population. So what this will do for us is it will tell us the fraction of people or things in this population that have a particular characteristic. This is easiest to see through example. So we're going to start with an example of a density function and look at the type of information that we have from this function. Then we'll go ahead and we'll define it a little more concretely. Example 1. Suppose the ages of people in a population are distributed as follows. So we have two pieces of infographic here. We have a table and we also have a picture. So let's talk about the table first. So in this population, there are people that are grouped in ages with 20-year spans. So everybody from age 0 to 20 is grouped together, 20 to 40, 40 to 60, 60 to 80, and 80 to 100. So in the second column, you'll see the percentage of the population that fits this characteristic. So that means 29% of the population has people ages 0 to 20, 29% of the population has people 20 to 40, 26% of the population has people 40 to 60, 13% of the population is 60 to 80, and 3% of the population is 80 to 100. Now, we need to talk about what happens right at the cutoff. So typically the way we think about this is for people ages 0 to 20, that's people ages 0 to 19 and 364 days. So the day right before they turn 20. So anything between 0 and that point. The day they turn 20, they graduate, if you will, up to the next bracket, 20 to 40. So anybody who is on their 20th birthday until the day before their 40th birthday would be in the next bracket, so on and so forth. So we can see percentages of the population, and this makes sense because the older you get, the less likely you are to be alive. So when we look at our graph, we see this represented in a different way. So notice that on the bottom, on the independent axis, we do have years that span in 20-year increments, 0, 20, 40, 60, 80, 100. But now on the dependent axis, we have the fraction of the population by years of age. So what that means is that for everybody from 0 to 20, let's say, that represents 29% of the population. But we have to take into account all the ages between 0 and 20. This model assumes that they're all equally likely. So that means the height for any given integer between 0 and 20 should be that 29% divided by 20. So remember, if we want to turn a number from a percentage into a decimal, we move it left 2 places. So we took the number 0.29 and divided that by 20, which is the length of the interval. 0.0145 is the height here. You can see it's almost 0.015. So that means that it's equally likely that someone is 1, someone is 2, someone is 3, and the fraction of the population at each individual age from 0 to 20 is approximately 1.45%. So when you add up all those ages from 0 to 20, you would multiply that number by 20, and that's where you got that 29%. So if we wanted to get the height from 20 to 40, it's going to be the same because that was the 29% divided by 20. From 40 to 60, however, we now need to take 0.26 or 26% and divide by 20, which will give us a height of 0.013. For 60 to 80, we're going to take that 13% or 0.13 and divide by 20, which is going to give us 0.0065. And then finally, from 80 to 100, we're going to take that 3% and divide by 20, which is going to give us 0.0015. So those are the heights that are being charted because each interval needs to be divided up by the length of the interval to get the height. So We now have a graphical representation of our population. We have a table representation of our population. And now we can answer some questions about this population. A, using the density function, determine what percentage of this population is between 20 and 60 years old. So in this particular case, it's going to be easier to look at our table to figure this out. So from 20 to 60 contains two intervals, both 20 to 40 and 40 to 60. So we can take these two percentages and add them together to get the total population that has this age range. So 29% plus 26% is going to give us 55% of our population. So 55% of our population happens to be between 20 and 60. Part B wants less than 10 years old. Now, this is a little tricky because 10 is not one of the numbers that is our cutoff. So let's go to our picture for a minute. Remember that all outcomes are equally likely. In this interval span of 20 years, that represents 29% of the population. Well, less than 10 is going to be half of that population. So we could either multiply our percentage, 29%, times half, which would give us 14.5%, or we could do this graphically. Because we know the height is 0.0145, then from 0 to 10, which is less than 10, is the area of that box, which is going to be 10 years times 0.0145 in height, which is going to give us 0.145, which as a percentage is again 14.5%. Because the area of these rectangles tells us the total population that we're working with. Let's see if we can apply this type of idea to parts C and D. So for part C, we want to know what percentage of the population is between 75 and 80. So first, if we look at our interval, we know that halfway between 60 and 80 is 70, but we're interested in 75, which is halfway between 75 and 80. So that's a 5-year span from 75 to 80. So what we can do is we can multiply 5 times 0.0065. Now, this is how we do it graphically to get that area of that rectangle. So when we do that, if we do 5 years, which is 75 to 80, times the height, 0.0065, we are going to get 0.0325, which, if we turn into a percentage, is 3.25%. Another way that we could have done this problem is we could have looked at our interval, 75 to 80. We could have figured out on our table which bracket that falls in. And then we could have said that 5 years is 1/4 of the population between 60 and 80, right? So 5 out of 20 is 1 out of 4. So we could have taken this 13% and multiplied by 1/4, and we would get the same answer. So we could have used the table data, or we could use the chart data, whichever one is easier for you to do. Let's look at part D. So between 80 and 85, we are now in the bottom row here of our data. So as I said before, if we want to use the table, we want to look at what number of years as part of the interval we're looking at. So again, this is 5 years out of 20. So 5 out of 20 is 1/4 times the percentage of the population that is there, which is 3% or 0.03. When we multiply those two things together, we are going to get 0.75%. Or if you had done that as a decimal, that's 0.0075. So it's very small. Similarly, we could have done a little picture over here, right? So 80 to 85, if we divide that up into fourths, is going to be this first chunk. So 5 years times 0.0015 would also give us that 0.75%. So this information is telling us about fractions of the population that have the characteristic of age. And we're able to use this information to talk about how many people are in these different categories. Let's see what happens when we refine our information and how that will change our outcomes. Example 2. Suppose that we have a better approximation for our population. And now we have a new table and we have a new picture that goes with it. It's the same data that we had before, but instead of representing it over 20-year spans, we can now break it down and represent it over 10-year spans. So I want you to remember, in the last problem we did, from 0 to 20 was 29% of the population. Well, if we look at what's happening from 0 to 20, it's still 29% of the population because it's 14% and 15%. Only now we know that it's more likely that someone would be between 10 and 20. So those still add up to the same things we had before. We're just further breaking it down so that we have a better understanding of where things lie. So we're going to use this information to now answer the same questions to see if we have a better approximation. We'll also compare it to the answers we had in the first problem to see if anything changed. Using the refined density function, determine what percentage of the population is between 20 and 60 years old. So as a reminder, when we were looking at example 1, we found this to be 55%. If we look at what's happening here, and we're looking at 20 to 60 years old, we have to include all the different intervals that span from 20 to 60. So here, that's going to give us 14% for the 20 to 30-year-olds, plus 15%, plus 15%, plus 11%. And when we add that all up, we get 55% of the population. Now this makes sense that it would be the same as example 1 because from 20 to 60 involves the same 20-year spans in 10-year intervals. So because we're just breaking the 20-year intervals up into smaller intervals, they should still add up to the same amount, which was 55%. However, when we look at our other questions, we'll see how we can get more accurate information. So part B wants to know less than 10 years old. So remember, before we just had to look at our 29% from 0 to 20 and cut it in half because everything was equally likely. Now, when we did this in example 1, we got 14.5%. Only now, if we look at our chart, we see that 0 to 10 years old is actually 14% of the population. So a little bit lower than we got in example 1 when we were estimating. Part C, again, wants to know what fraction of the population will be between 75 and 80 years old. So again, what we can do is we can go to 70 to 80, which includes the interval we're interested in. It's a 10-year span, but we're interested in 5 of those years. 75 to 80 is 5 years out of 10, so we can take that 6% and multiply by 1/2, or 5 over 10. So that's going to give us an approximation of 3% here. In example 1, we got 3.25%. So we've actually made our approximation better because our interval is smaller. And then finally, 80 to 85, we can see that 80 to 90 represents 2% of the population. So if we're interested in 80 to 85, that's 5 out of 10 years, or half. So we multiply our 2% by half, and we get 1%. Now you'll notice that I did all my work on my table here, and I didn't use my graph, and that was mostly for the sake of time. If I wanted to use my graph, I would need to take each of my percentages and divide by 10 to get the height of each of my blocks here. And then I could do what I did in example 1 to get the same answers. Both methods are completely valid, so whichever one you prefer is totally fine. But one of the main takeaways here that's really important is that the more refined your information can be in terms of how big your intervals are, the more accurate you are. So if we can make our intervals smaller and smaller, our information becomes more and more accurate. So if we had a way to measure every 5 years, that would be even better. If we could measure for every year, that would be optimal. So the larger your intervals are, the more likely you're approximating to get your answer, and the smaller your intervals are, the better your approximation is. So the types of graphs we've been looking at have a special name. They're called histograms. A histogram is a diagram consisting of rectangles whose area is proportional to the frequency of a variable and whose width is equal to the class interval. So what that means is that we are looking at the area under the curve to give us the percentage of the population who has a specific characteristic. In the example we looked at before, that characteristic was age. And so the area of the rectangle told us what percentage of the population was of the age that was defined by the interval on the bottom. So if we look at the pictures of what we had when we had 20-year intervals versus 10-year intervals, what I want you to notice is that the area that it's representing, if we were trying to graph it as a function, looks different depending on the intervals. So let's connect these midpoints and see what I'm talking about. So the histogram here, if we look at the midpoints, gives us a function that roughly looks like that. It's not smooth and it's not perfect, but that's roughly how things are distributed based on the picture we have. When we shrunk the intervals down into 10-year intervals, what happens is our histogram starts to smooth out a little more and become more accurate into what's going on. You can see that there's more bumps and waves when we have 10-year intervals. Ideally, we would keep shrinking our intervals, and then once we got down to 1-year intervals, we would have an exact approximation of what our function actually looks like. So these histograms are important because we often use them to figure out fractions of the population. And again, you've probably made the connection that the area under these curves, these histograms, are really important. And we know how to find area under the curve by using our integration techniques. So now that we've explored this example, let's look at what some of the properties of density functions are. The function little p of x is a density function if little p of x is always greater than or equal to 0 for all x. So the things that we measure should only have positive values. The integral from negative infinity to infinity of little p of x dx equals 1. So that means if you calculate all of the area under the curve for all of time, it should equal 1, which represents 100% of the population. So this should make sense. It should always integrate to 1 because, again, we're talking about percentage of the population, and every population we look at, we're looking at the entire thing, so 100% of it. And the integral from a to b, so between 2 points, of little p of x dx represents the fraction of the population for which x, the characteristic, is between a and b. So if we want to know how much of the population has a particular trait, we would look at the area under the curve between a and b, or the interval that represents the trait that we're looking at. So these three properties together are really important. So if any one of them fails, then we don't have a density function. So some of the types of questions we're going to look at are just making sure that the functions we're looking at are actually density functions. Now, I really want to point your attention to the fact that we're using little p here to talk about density functions. Later on in the course, we're going to talk about what happens when you integrate this and we have a capital P. So the distinction that this is lowercase is important to remind us that what we're looking at is a density function and therefore has these three characteristics. So let's see what ways we can use these characteristics to talk about and look at different density functions. Example 3. Suppose that little p of x equals k times square root of x on the interval 0 to 4. Find the value of k for which this is a density function. So notice that our x values go between 0 and 4. So that means that the square root of x will be positive as long as k is positive, or equal to 0. So the first part of our density function features is satisfied as long as k is positive. That means that our p of x will also be greater than or equal to 0. The second part of this is that if we integrate this over the bounds negative infinity to infinity, it would have to equal 1. However, we are restricted to a certain domain, 0 to 4 here, which means that we can modify our second point here, and we can make sure that if we integrate from 0 to 4, that our function equals 1. So this is the bullet point that we really need to use here in order to solve this problem. So here we're going to go from 0 to 4, which is our entire domain, of k times the square root of x dx. And we know that in order for it to be a density function, that has to equal 1. So we want to use what we know about integration and antiderivatives paired with the fundamental theorem to find the antiderivative of this function. So if we come up over here, remember that if you have the square root of x, that's the same thing as x to the 1/2. And so the antiderivative here, we're going to add 1 to the power to become 3/2 and divide by the new power. But if we divide by 3/2, it's the same as multiplying by 2/3. And we're interested in this function from 0 to 4. So when we plug in a 4 to the 3/2, that means we're going to take the square root and then cube that number. The square root of 4 is 2, and 2 cubed is 8. So that 8 is going to be combined with the 2/3 to give me 16/3 k minus, now if I plug in the lower bound of 0, I get 0. And I know that since it's a density function, that has to equal 1. So now, if I want to solve for k, I'm going to need to multiply by the reciprocal of the fraction that's in front of k to get rid of it. So I multiply both sides by 3/16, and I get k equals 3/16. So when k equals 3/16, that means our function will be positive for all x, which is our first condition because k was positive. And if we integrate our function from 0 to 4, which is where it exists, and our k is 3/16, that will give us a value of 1, which means it represents 100% of our population, which is what we need for this to be a density function. If we wanted to know the size of the population between any 2 points, they would have to be between 0 and 4 because that is where this exists. Now, this particular function, we don't know what it models. It didn't say. We don't know if it's age, we don't know if it's IQ, we don't know if it's numbers of hours of sleep. There's lots of characteristics it could measure, but we don't know because it wasn't given to us in the problem. However, we do know how to ensure that it is a density function by making sure that our first 2 rules are adhered to ensure that this follows what we need to be true for it to work. So when you're asked to make sure something is a density function, these are the 2 things that should come to mind. The third bullet point under density functions is just another way of talking about how we are going to be calculating different characteristics. So we'll look at that third bullet point in the next example. The density function for the length of stay at a vacation resort in June is given in the graph below. So let's talk about the information we have in this picture. Notice that the shortest amount that any guest stayed was 4 days, and it looks like the most anyone stayed was about 19 days, because that's where our endpoints hit from our picture. We can figure out what proportion of people stayed for various lengths of stay by looking at the area under the curve. Now, notice that this is a pretty bumpy curve. It's not as nice and rectangular as before, which means that our histogram has been smoothed out, and this is an accurate representation of all possibilities. The area under this curve has to represent 100% of our population. We want to know how many guests stayed from 10 to 12 days, which means that we would need to find the integral from 10 to 12 of our density function. And if we're doing this on a graph, we're going to have to do some really good estimating here. So 10 to 12 is this chunk of area here. So in order to approximate the area under the curve from 10 to 12, what I'm going to do is I'm going to figure out approximately how many blocks I see that would represent the area, and then I'm going to find the area of one block, and then I can multiply those two numbers together. So I'm pretty satisfied saying that there's approximately 4.5 blocks under the curve. So 1, 2, 3, 4, and then there's a little half a block here. So 4.5. But I also need to know what one block represents. So if I come over here to the origin, I notice that the width of my block is 2 units and the height of my block is 0.03, which means that any one block will do width times height is 0.06 in area. That's important because I'm saying that there's 4.5 blocks between 10 and 12 days. So I have to multiply that by 0.06, which is the fraction for any one block. So if I multiply those two numbers together, I'm going to get 0.27, which means that approximately 27% of guests stay between 10 and 12 days. So I'm saying approximately because, again, I'm approximating the area under the curve. It's not an exact science, and that half might actually be something like 0.45, but approximately 27% of patrons stay between 10 and 12 days. If I wanted to know other lengths of stay, I would use the same process by approximating how many blocks were there and then multiplying by 0.06 because that is the area of one block. So we can use this method when we have pictures, and that pairs up with our third property that said to find the area between 2 points, look at the area under the curve. So let's try another example that's going to require us to think about density functions and how we put them to use. Example 5. The distribution of the height x in meters of trees is represented by the density function p of x. Use the diagram below to find the fraction of trees that is less than 5 meters high. So first we want to make sure that our two really important rules are satisfied. First, our function needs to be positive or 0. So here we can see that our density function is strictly above the x-axis, starts at 0 and goes as high as 0.1. So it's definitely not negative here. So that's good for us. Secondarily, we need to make sure that the area under the curve equals 1 to make sure we're representing the entire population. So if we look at the area, it's going to be a triangle. So notice that we could do 1/2 base times height to make sure that that is satisfied. So our base is 20, our height is 0.1, and if we multiply those together, we do get 1. So 100% of the tree population is represented. So this is a density function, and we can proceed in talking about different factors here. We want to know what percentage of this population is less than 5 meters high. So let's think about where 5 is. So 10 is going to be around here. So 5 is going to be here. So the area that we're interested in is this area here, less than 5. So between 0 and 5, since we started at 0. So if we knew the height at 5, we could certainly use geometry. We could do 1/2 base times height. But we don't know the height. If we knew the density function, the formula for it, then we could integrate it from 0 to 5, but we don't know that yet either. So we're going to have to figure out one of these two things in order to be able to proceed. The easiest way to approach this is to find the formula for the density function. Notice here that our formula is going to be linear, right? Our density function is represented by a line. So if we want to get the equation of a line, we can use 2 points on that line to get the equation. Fortunately for us, we have 2 points on the line. This line goes to the origin, which is 0, 0. And we know the point when x is 20, y is 0.1. So we have these 2 points on our line, and so the first thing we want to do is find the slope of the line. The slope is change in y over change in x, so 0.1 minus 0 divided by 20 minus 0, and we get a slope that's equal to 0.005. Now, remember, the equation of a line is y equals mx plus b. We have the m, but what about the b? Remember that b is your vertical intercept. It's where the line crosses through the vertical axis. Well, here it crosses through at 0. So therefore, b is 0. And the equation of our line is then y equals 0.005x. That's our density function. That's what models what we're looking at. And it only exists from 0 to 20. That's where we stop. So we have a restricted domain. So if we want to know how many trees are less than 5 meters high, we can certainly use our third function of density functions and integrate from 0 to 5. We're going to integrate our density function, 0.005x dx. This is a definite integral, so we can either do it by hand or we could plug it into the calculator. Either way would be fine. And we will get 0.0625, or equivalently 6.25% of trees are less than 5 meters high. If we had wanted to do this geometrically, what we could have done, again, is 1/2 base times height, and we have 1/2, my base is 5, and now my height here, I could get by plugging 5 into my function to get the corresponding y value. If I plug in a 5 there, I'm going to get 0.025 as my height. So 0.025, so 1/2 base times height will give me the same 0.0625. I find it easier to use the integral, but you can certainly use geometry, but either way you have to find the equation of the line. So let's look at part B. Part B asks us to find the fraction of the trees that are less than 6 meters high. Well, this is the same function as before, so we know the equation of our line. So again, we can set up an integral from 0 to 6 of 0.005x dx. And if we were to integrate that, we are going to get 0.09, or equivalently 9%. So remember, before we did less than 5, now we're looking at less than 6, which is still a triangle. Previously, we wanted to know what percentage of trees were less than 5 meters high, which was 6.25%. This question asks, how many trees are less than 6 meters high? We can see that 6 is to the right of 5, and therefore we're expecting our answer to be a bit bigger, and it is, coming in at 9%. Again, if you prefer not to use the integral and you would like to do 1/2 base times height, you can. So here we do 1/2, my base is 6. To get my height, I'd have to plug a 6 into my density function here, so that's 0.03, and that would also give me this 9%. So again, you can set up the integral, or you can use 1/2 base times height. Part of the reason that I encourage you to use the integral is because not everything is going to always be linear, and being in the habit of using the integral is good. But for this particular case and other linear cases, we could certainly do things geometrically. Let's look at the next part, which is related to this part in an interesting way. Part C asks you to find the percentage of trees that are more than 6 meters high. Well, we just looked at what percentage of trees were less than 6 meters, and we said that that's 9%. 0.09. Now, first let's talk about how we would set up our integral, and then we'll talk about another interesting way we can approach this problem. So our integral here, more than 6 meters, would go from 6 to 20, because remember, our domain was 0 to 20 here. That's how we calculated this original part where the area was 1. So 6 to 20 of our density function, 0.005x dx. When you plug that into your calculator or you do it out by hand, you get 0.91 or 91%. Now, you'll notice that more than 6 meters is a trapezoid. So you could certainly figure out the area using geometry. However, if we want to find the percentage of trees that are more than 6 meters high, and all trees either have to be less than 6 meters or more than 6 meters, what we could have done is we could have done 1, which is 100%, minus the percentage that was less than 6 meters, which gives us the remaining percentage of trees, which was 91%. So if you're looking for the opposite of something you have found, you can subtract it from 1 to get the complementary fraction of the population, as long as the two complements represent the entire population. So for part B, we found the percentage that was between 0 and 6 meters high, and now we're trying to find 6 to 20. So those are complements because it represents the entire population. So we can do 1, which again represents 100%, minus 9%, which would give us the 91%. We don't have to, however, because we can just stick with our integration if you're comfortable with that. Finally, let's look at a percentage that doesn't include one of the endpoints. Part D. Find the percentage of trees that are between 2 and 5 meters high. So notice now that I'm not using 0 as a starting point. And so again, I'm looking for this area that's trapezoidal in nature, or you can break it up into a rectangle and triangle if you were to approach this geometrically. However, the area between any 2 points can be found using integration. So here we're going to integrate from 2 to 5 of our density function, which is 0.005x dx. If we plug that into our calculator, we are going to get 0.0525 or 5.25%. So 5.25% of trees are between 2 and 5 meters high. So again, the key for all of these problems was first finding the equation that represented our density function. We were then able to find the fraction of our population that met our requirements by looking at the area under our density curve by using integration and antiderivatives. So far, what we've been looking at is what fraction of the population meets our requirements. There's a way that we can reword this type of problem to be used in a different way, although the math is going to be the same. So one subcategory of density functions, which again is going to look at this pretty much the same way, is something called